I'll be building a iron carbon cell for you today, and as you'll see, it's very simple. There's nothing complicated about it. As I've mentioned in my previous video, it uses steel wool as the iron source for the negative electrode, and carbon felt as the positive electrode. And over the course of these videos I may refer to them as electrodes or active materials. Electrodes are more accurate, but habits die hard. Anyway, we'll get into why I don't think this carbon is actually or should be considered part of the active materials. In any case, as I said, carbon positive electrode, steel wool for the iron for the negative electrode, and I'm using an acrylic felt. It's also referred to typically as craft felts, although this particular one is acrylic, as the separator. Two plastic plates, plexiglass or acrylic plastic works well. They're just to sandwich the entire cell together. The current collectors in this case are graphite foil. This is a 1/32 of an inch thick graphite foil. For this cell you can use graphite or titanium foil. I've got both. Graphite's a little bit more, a little less expensive, more disposable, and it unfortunately has a tendency to break down relatively easily under any kind of mechanical stress. And it's also more difficult, I find anyway, to get a decent electrical connection to it, but nevertheless it works fine. What I'd like to do is to weigh the active materials, or the electrodes in this case, just to give you a sense of the masses we're dealing with here. And I've just got an inexpensive little scale here that's adequate for this particular task. Now I'll zoom down on that so you can see that. So that's reading 1.06 grams for the carbon felt. And 1.04 for the steel wool. So practically it's 2 grams of electrode material, active material if you will, and as I showed in the previous video, that basically gives us a cell that will output about 260 odd milliwatt hours, and for that weight of electrode slash active material, if you will, I still find that a relatively decent output given the mass of these elements of the cell. Okay, well, let's get on with it then. I start with one of the acrylic plates. We simply place on top of that one of our graphite foil pieces. In this case it's the negative, as it doesn't appear to be picked up by the camera, but anyway, I've got this marked negative. Now I'm bringing in here my iron 2 chloride electrolyte, and I mentioned previously that I find the iron 2 chloride a little bit more manageable in terms of the chemical reaction or lack thereof between the steel wool and the electrolyte. If I had done the same thing here with iron 3 chloride, and I probably should demonstrate that, but we'll save that for another time. This little plastic container will literally just melt into a puddle. So what I've done here is just soak the steel wool in the iron 2 chloride. I'll do the same with the separator. This is a flooded cell. Some refer to them as wet cells. It is basically both electrodes and the separator are completely wetted with the electrolyte. And again, the same with the carbon felt. Now there are, and I'll do a video about how to actually improve the output of this cell. There's a variety of things that will improve it, such as treating the carbon felt with an acid that I think essentially the proper term is, to one degree or another, functionalizes the felt. I have experimented with that, and there is actually a pretty reasonable increase in performance once that's done, but I'll leave that for another time. And then simply the other current collector, followed by the other plate, and squeeze off the extra electrolyte. And I am aware that my choice was to wear gloves, but unfortunately I've run out of them, and given the current virus situation, I'm unable to get any more where I happen to live. So there we go. We now have a completed functional cell that's 2 inches by 2 inches, 5 centimeters by 5 centimeters. That gives us obviously an area of 25 square centimeters, and that will give you 260 odd milliwatt hours over an area of 25 square centimeters, or 4 square inches. Now I've shown that running, not this cell, obviously. This is one that I've just built to demonstrate how it's put together, but the previous cell was constructed in exactly the same way. And I've also mentioned, I believe, that when you use iron 2 chloride as the electrolyte, you don't get any immediate action at all. If that was iron 3 chloride, you would have enough power to drive this motor for well, if not an hour, certainly a good chunk of that. And it's really the difference between building this cell in a charged state versus an uncharged state, and this is really the uncharged state. And I'm stacking up subjects for videos, but I will do one on the chemistry as I understand it with respect to the cell. But we'll leave that for now. So that's the construction. What I'm going to follow this video up with is a demonstration of, or an experimentation perhaps, of with the various load currents that this thing can output. It's akin to a short circuit test. These cells on a straight short circuit test with a with a multimeter for a short duration, something like 10 or 20 seconds, they'll generally output somewhere in the order of 2 amps at well, not a significant voltage, something on the order of 0.2 or 0.3 volts when they're loaded. The nominal voltage for this cell is a volt. Generally on a fully charged battery it'll sit there with a voltage of about 1.2 volts. But once you load it, that generally drops to a volt. The only other thing that I actually wanted to mention while I was making this video, I have here the internals from an earlier battery. In fact, this was the battery that I ran and gave it ran in the first video to show the approximately 260 milliwatt hours. This is the carbon felt side of the this active material stack. This is the carbon felt, the separator, and on this side is the steel wool. Now you may be able to see how thin this all is. It's basically compresses down to a fairly, once it's been run, a very thin structure. The steel wool essentially certainly, I'm not sure how well the camera will pick this up, but the steel wool has essentially been transformed really into a gray iron paste, and essentially the fibrous nature of the steel wool itself is completely gone. And this is the way the cell operates. Very shortly after the first couple of charges, the steel wool is completely converted from steel wool into this really what is an iron paste. Now there's also carbon in here because I'm using steel wool, and steel wool it is a carbon steel, and therefore there will be a carbon component to this. That really doesn't play any role in the chemistry or in the operation of the cell, but very quickly, with the first few discharge cycles, the steel wool gets broken down. There was a suggestion from a few people that the steel wool would break down into rust. That's not really the chemistry that's going on here in the iron carbon cell with respect to having an iron 2 chloride electrolyte. Really, the iron of the iron carbon battery converts to iron 2 chloride and back to metallic iron on the negative electrode, and on the positive side, the iron 2 chloride is converted to iron 3 chloride and back as it's charged and discharged. So, as I say, I'll speak more about the actual chemistry as I understand it in a later video. So I wanted to show that, just in that there's certainly no rust evident here, and it does not develop over the operation of this cell. And the other thing I did want to mention is that this particular internals, they've been operating for about a month now, and that's a significant number of charge-discharge cycles. And essentially, it's good to go as it is, and the iron doesn't really change in any significant way beyond where it is now. And of course, the carbon felt is innocuous, or it does not take part in any of the chemistry that's actually going on in here. Okay, well, that's it. I've now shown you how to build the cell and what happens to the internals once it's been charged and discharged a few times. Thanks.